Want to ace tree questions at Google, Amazon, or Apple? Binary Tree Level Order Traversal is a classic pattern mastery 100 question. And over 25% of candidates mess up the queue logic or output formatting. Nail this one, and you'll be ready for everything from graph traversals to real-world scheduling challenges. Let's level up your skills together. Let's solve binary tree level order traversal with the basic method, so you build rock-solid, interview-ready solutions every time. Let's break this down. Given the root of a binary tree, return its values level by level, that is nodes at each depth together in a list. Input, root node of a binary tree. Output, list of lists. Each inner list contains all node values at that tree level. Here is an example. Input, output, 3, 9, 20, 15, 7. Here is a real-world example. Suppose you're managing a project with tasks organized in dependency levels. You want to group tasks by which ones can be started at each phase. An interviewer might ask, how would you organize a company's org chart into management levels for communication planning? Now let's assess it. What's tricky? This is a classic breadth-first search, BFS. You need to process the tree layer by layer. You need a queue to keep track of which nodes to process next. The result must be grouped per level, not just a flat list. Think step by step. If the root is null, return an empty list. Initialize a queue with the root node. While the queue isn't empty, track the number of nodes at the current level. Queue size at start of a loop. For each node at this level, pop from the queue, add its value to a temporary list. Add its left/right children to the queue for the next level. After finishing this level, append the temporary list to the final result. Repeat until all levels are processed. Let's add more detail. Why track the queue size at each loop? It ensures that you process exactly the nodes at the current level, so your output matches the level grouping. Forgetting this step is a classic source of bugs. Some edge cases. Empty tree. Return. Single node. Return. Val. Deeply skewed or unbalanced trees should still work. Here is the structure. If root is null, return. Initialize a result list and a queue with root. While queue not empty, get current level size. For each node at this level, pop, save value, in queue children. Add this level's line highlighted. Class solution. We start with our solution class, the container for our level order traversal logic. Line highlighted. Public list integer level order tree node root. This method will return a list of levels, where each level contains all the values in that layer of the tree. This is a classic breadth-first search, BFS, pattern. Line highlighted. List integer result equals new array list. We create an empty list that will eventually store all levels of the tree. Think of it as a notebook where each page represents a level. Line highlighted. If root equals null, return result. If the tree is empty, we return an empty list immediately. No levels exist, so there's nothing to traverse. Initialize BFS. Line highlighted. Queue tree node queue equals new linked list. We use a queue to process nodes level by level. A queue works perfectly because it follows first in, first out order, just like students lining up at a cafeteria. Line highlighted. Queue.offer root. We begin BFS by placing the root node into the queue. Process the tree level by level. Line highlighted. While !queue is empty, the loop continues until every node in the tree has been processed. Line highlighted. Int size equals queue.size. We capture how many nodes are in the current level. This is important. It tells us exactly how many times we should loop to complete this level before moving to the next. Line highlighted. List integer level equals new array list. This list will store all values found in the current level. Process each node in the current level. Line highlighted. For int I equals 0, I less than size, I++. We iterate exactly size times, ensuring we process only the nodes belonging to this level. Line highlighted. Tree node equals queue.pull. We remove the next node from the queue, pulling from the front, just like FIFO. Line highlighted. Level.addNode.val. We record the node's value in our current level list. Add the node's children to the queue. Line highlighted. If node.left equals null, queue.offerNode.left. If the node has a left child, we add it to the queue so it will be processed in the next level. Line highlighted. If node.right equals null, queue.offerNode.right. Same idea. If there is a right child, it's added to the queue as well. Line highlighted. End of our loop for this level. Store the completed level. Line highlighted. Result.addLevel. We finish the level and record it in our master list. Line highlighted. End of the BFS loop. At this point, all nodes from all levels have been processed. Line highlighted. Return result. we return the complete list of levels. Line highlighted, this closes the method. Line highlighted, and this closes the class. Time complexity note. This level order traversal touches each node exactly once, and each node is added and removed from the queue once. That gives us ON time complexity, where n is the number of nodes in the tree. Final wrap-up summary. And that's how this algorithm works. It first initializes a queue with the root node, then processes each level by checking the current queue size and expanding children into the next level. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth-first traversal should produce. Highlight output box. Output, 3, 9, 20, 15, 7, expected, 3, 9, 20, 15, 7. And the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Let's try to implement it using Solution 1, but now narrating Solution 2, the DFS-based level order traversal. Line highlighted, import java.util. We import Java utilities because we need lists to store levels. Line highlighted, class solution. We begin the solution class, which contains our DFS-style level order traversal. Level order using DFS. Line highlighted, public list integer level order tree node root. This method returns all nodes grouped by their level, but instead of BFS, we do it with DFS. Line highlighted, list integer result equals new array list. We prepare a list where each index represents a depth level in the tree. Line highlighted, DFS root, 0, result, we start a recursive depth-first search, beginning at depth 0. Line highlighted, return result. Once DFS finishes, we return the filled list of levels. Line highlighted, end of the level order method. DFS helper method, line highlighted, private void DFS tree node, int depth, list integer result. This helper method visits nodes using DFS and assigns each node to its correct level based on the depth parameter. Base case. Line highlighted. If node equals null, return. If the node is null, there's nothing to process, we return. Pause. Ensure the list for this level exists. Line highlighted. If depth equals result.size, this line checks if we are visiting a level we haven't seen before. If the list doesn't yet have a sublist for this depth. Line highlighted. Result.add new array list, we create a new level list. It's like opening a new page in a notebook for this depth. Add the current node to its level. Line highlighted, result.getDepth. Add node.val. We add the node's value to the list corresponding to its level. Go deeper into left subtree. Line highlighted, DFS node.left, depth +1. Result, we recursively process the left child at the next depth level. Then right subtree, line highlighted, DFS node.right, depth +1. Result, and then recursively process the right child at the next depth level. Line highlighted, end of the DFS helper method. Line highlighted, end of the class. Time complexity note, each node is visited exactly once, and each visit does constant work. Therefore, DFS level order traversal runs in ON time. Final wrap-up summary. And that's how this algorithm works. It first prepares an empty result list, then uses DFS to visit each node and place it into the correct level based on its depth, creating new level lists as needed. Efficient, structured, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth-first traversal should produce. Highlight output box, output, 3, 9, 20, 15, 7, expected, 3, 9, 20, 15, 7, and the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Let's quickly recap binary tree level order traversal, a must-know interview question that tests your understanding of queues and BFS traversal. The goal was simple: traverse a binary tree level by level, grouping nodes at the same depth together into lists. Essentially, we built a layer-by-layer view of the tree. We recognize that breadth-first search is the perfect fit, using a queue to process nodes in order, one level at a time. The key challenge was keeping track of the queue size each round, so we only process nodes from the current level. Our plan: check for an empty tree, initialize a queue with the root, loop until it's empty, collect values for each level, and in-queue child nodes for the next round. We wrote this logic step by step, using a clean BFS loop and a result list, and it ran smoothly on LeetCode without any errors. We verified the output, each level printed correctly, from top to bottom. 3, 9, 20, 15, 7. Edge cases like empty or single node trees worked perfectly. The big takeaway? Queue-based BFS isn't just for trees, it's the backbone of level order logic in graphs, scheduling systems, and even social network distance calculations.